Hello, I'm Doug Montgomery, your course instructor for the Design of Experiments course, and I'd like to welcome you to our March 2022 Fireside Chat for the Design of Experiments specialization. For those of you that are new to this, either the Coursera course or to the Fireside Chat, this is an event that I try to run every month. And I always have a guest speaker, and I ask our guest speaker to give a presentation about some of the things that they're involved in that can involve experimental design. And it's an opportunity for us to explore some specific topics and applications in a little bit more depth than we sometimes do in the formal part of the course. I always like to leave some time at the end for questions and answers from you. This is a great time for you to ask any questions that you would like, whether they are about the Coursera course or they're about the presentation that our guest gives, or some specific situation that you're involved in that you're trying to think about applying design of experiments to. And perhaps that either me or the guest can give you some ideas about that. And so if you have questions, the best way to get those to us is to post them in the chat feature on Zoom, and then we'll be able to get to them at the end of the Fireside Chat. If we can't get to everything that comes in, or if sometimes if the answer is a bit more involved than we can really get to during the Fireside Chat, we'll try to take care of answering those offline, and then we'll get that information back to you as quickly as we can. For those of you that are on Coursera, these Fireside Chat recordings are posted in the resources tab of your course, and all of them are there. And so you can look at not only the one today, but you can go all the way back to the beginning of time, or whatever the beginning of time was for this course. And you can see all the Fireside Chats. There's a lot of very interesting ones. And so let's get going with today. I got just a couple of quick reminders. Please keep your microphones muted, keep your cameras off, so that we don't have any excess noise or any other disturbances that will detract from the Fireside Chat. But with that, I think we've covered just about everything. My guest today is Dr. Pete Parker, who is the team lead for advanced measurement systems at NASA. And he is at the Langley Research Center in Hampton, Virginia. He has a BS in engineering, an MS in applied physics and computer science, and an MS and PhD in statistics from Virginia Tech. So he's also a Hokie. He serves as an agency-wide statistical expert across NASA's aeronautics, exploration, science mission directorates. And his job is infusing statistical thinking, engineering, and methods. He spent 8 years in private industry. He's been with NASA, Langley Research Center, starting in 1997. Peter is an associate fellow of the American Institute of Aeronautics and Astronautics, a senior member of ASQC, and American Statistical Association. He's past chair of ASQC's Publications Management Board, Journal Editors Committee. He's editor emeritus of Quality Engineering, and he currently serves as the chair of the International Statistical Engineering Association. And it's my great pleasure to have Pete with us today. He's a very busy guy, and for him to take time to spend with us is really a great pleasure. And he's going to talk with us about statistical applications and experimental design things that he's seen at NASA. So Pete, the floor is yours.
Great. Well, thank you very much for that introduction. And let me bring up my slide. Hopefully you're seeing that. We're good.
Yep. Looks good.
Excellent. All right. Well, thank you, Doug, for inviting me. And today I'm going to share about some of my experiences with design of experiments at NASA and tell a little bit of my story of how I got involved with design of experiments. But first, let me tell you a little bit about where I'm from, which is NASA Langley Research Center. Sometimes when you think NASA, you think of the centers where you see the launches in Florida. I'm from a center that actually has over 100 years of history and predates the formation of NASA. It's one of 10 NASA centers, and it was originally established in 1917 under what was then called the National Advisory Committee on Aeronautics, NACO. And in 1958, when President Eisenhower created NASA, we were one of the first NASA centers. We are the home of the initial astronauts, the Mercury 7. If you watch the movie Hidden Figures, you might recognize the large airplane hangar in the picture in the upper left in the foreground. That's where the shot was taken when the astronauts came and greeted the Space Task Group in that movie. And that movie is set in Hampton, Virginia. That's the center that I work at. In the background of that picture, you probably can't quite make it out, but there is a facility where Neil Armstrong practiced landing on the moon. So that's just a few miles from my office. And, all of this together is that we have a very proud history at Langley, a long history. And today we focus on sort of all of NASA's big mission directorates, which can be divided into space. That's both human and robotic exploration, aeronautics, which involves the aircraft design, as well as things like air traffic control systems, next generation airspace, the national airspace. We work in those areas. And then we work in atmospheric sciences that involve both our own Earth, our own planet, as well as other planetary. And I'm going to give you a little sprinkling today of design of experiments across all of those areas and experiences that I've had. Before I start my story, I've got to tell you a little bit about a condensed story of NASA, and particularly how NASA's aerospace development has developed concurrently with the field of design of experiments. Now, I have a whole talk on this that I developed for the 50th anniversary of Apollo. I'm going to give it to you in one slide. So on the far left, we have a picture of the upper left of the Wright brothers flyer. That's the first sustained flight of a powered, heavier than air aircraft, December 17th, 1903. And if you know some history, and I know Doug does, Langley, who my center is named after, also had some forays into flight around that time, and a lot of interesting history that comes after that. But Samuel Pierpont Langley was also involved at that time. The bottom left, the picture that looks like a giant Tylenol, is the first wind tunnel at NASA Langley that was a variable density tunnel. So this was actually being delivered there on a railroad car from Newport News Shipbuilding, a short distance from our center. And it provided much more accurate performance testing at pressure. That was the big idea. Designed by a German engineer in 1920 and built and delivered in 1921. Now below that, I've kind of got this red timeline. So, when I was developing this story for the 50th anniversary talk I gave, Doug's actually the one that put the words that in that early days of flight, they were Edisonian. They just tried a lot of things. They were developing the first principles and understandings of flight. And to be fair, we look back at Ronald Fisher's work with agriculture in the 1920s as a marker for design of experiments. So it was kind of being co-developed, in that time. And so they wouldn't have been aware of all of the resources we have now today about the mature discipline of design of experiments. So let me move now to the middle. Well, I mentioned in my intro that NASA was formed in 1958, and I'm going to take a quick little foray here into the Army and make a link to that rocket you see sitting in the middle. So in 1955 was the first conference on design of experiments in Army research. Very long history. That conference was attended by big names like Jack Uden and Churchill Eisenhart and Stu Hunter, and had representation from the National Bureau of Standards, which is now NIST. It had representation from Bell Labs, Johns Hopkins, Virginia Tech, in fact. And it was focused on providing design of experiments technology to Army testing facilities, testing research facilities. And now here's the link. In 1956, the Army Ballistic Missile Command was formed. And that was, the first technical director was Warner von Braun, a very interesting historical figure. You can go back and look. Huntsville, Alabama, which is now where Marshall Space Flight Center is. And von Braun is actually the designer of the Saturn V rocket that you see in the middle in the picture. He was also the one behind the launch of the first satellite from Redstone Arsenal, the Redstone rocket. And so in 1960, the Army Ballistic Missile Command became part of NASA. And so there's a design of experiments link there with the Army that coincides. And now what's going on in sort of the design of experiments literature? Well, 1951 is when George Box publishes his paper that is considered kind of the start of response surface methodology, you know, which is, if we can think of that as an adaptation of design of experiments principles in an industrial context where you have immediacy of response and those types of things compared to long growing seasons in agriculture. That's one thing that made it different, but you know, that's 1951. So there's my center column kind of coinciding in the 50s for you. In the upper right, we have, of course, one of NASA's most famous accomplishments, the Apollo 11, first human on the moon, 1969. And when I was studying for this, I found a paper, it's referenced at the bottom, that was published in the American Statistician, that talks, well, the title of the paper, Some Statistical Applications in the Apollo Program. And the quote that I have in the middle came from that paper in 1966. And it said, most statistical work is performed by engineers and scientists, some well-trained in statistics and others having only a passing acquaintance with the subject. Well, I'm going to sort of give you a little hint. This is going to lead into my story on the next slide. And so while there was, you know, a tremendous technological advancement there, there was actually no position called statistician that this paper pointed out in 1966 during Apollo. And then to sort of fill out the era, I have the space shuttle, which just celebrated its 40th anniversary of first flight in 1981. And at the same time, we have sort of Deming, Taguchi, the quality movement in the 1980s. I think, and I'm sure Doug could speak to this a lot better than I could, that was really an era where design of experiments, along with other industrial statistics tools, became very prevalent in that era in the 1980s. Now, you know, I've told you this story, and I want to go back to the passing acquaintance quote and tell you now my story. I call it the engineer's statistical awakening. So traditionally, engineers lacked relevant, applicable, practical, interesting, I'll throw in there, courses in statistics. And that was me. You heard my undergraduate degree is in mechanical engineering. I took one statistics course and it was awful. I don't know any other way to say it. It was just awful. It was dice and card games. And I thought, what in the world am I ever going to do with this? You know, it was watered down math stat. And engineers are generally trained to fear uncertainty. It's something that keeps you up at night. I mean, you want everything to be deterministic. We want to know the answer to 6 decimal places. That's the way engineers are trained. I'll give you a quote from an engineer at NASA Langley, who will remain unnamed, who said, replication causes error. If I run the same experiment twice, I will get a different answer. Now, did the replication cause the error, or did it reveal error and then empower you to make more decisions better informed by uncertainty? And that's kind of the mindset of an engineer, at least of my era. I will say things have changed quite a bit. So in 1999, I stumbled upon a report that was already almost 20 years old. It was written by a visiting professor from a statistics department at NASA, and it contained these radical ideas. And they promised these orders of magnitude reduction in time and cost. And I was mesmerized. I mean, I thought this was pure innovative genius. What it was simple application of a central composite design, a very common design and response surface, a factorial structure, but I had never seen one before. I mean, uh, in my training, I had never seen one. And so what are some of those radical design of experiments concepts? Well, first is that experiments don't start by collecting data. They start by research questions. And I'm going to have a little more on that later. You know, that's a radical idea for an engineer who's just focused on collecting data. Factorial experiments. Well, if you had told me we were going to change more than one factor at a time, I would have said that's chaotic. The idea that that's efficient is a radical idea, which we now know very well for those of you who have been in this course. And modeling involves things like estimation of coefficients and testing those coefficients as to whether we can determine that they're non-zero. It's more than just plotting the data and drawing a line in between it. So all of those together is what I would say where I discovered new powerful techniques that really design of experiments is about efficiently learning. It's about gaining knowledge efficiently with uncertainty considered into it and getting deeper insights about system performance in ways that you cannot do any other way. Now, all this led me to go off and get graduate degrees. And you've heard in my intro, my master's and PhD in statistics at Virginia Tech, working with Jeff Feining, having the privilege to meet people like Doug Montgomery. And, all of that came. Now, beyond that, in my career at NASA, adding that in my tool set has allowed me to work on everything from aeronautical research of micro UAVs to helicopters to hypersonic flight. I've worked on everything from Earth's atmosphere to landing on Mars. I've had the privilege to work on NASA satellite data and models to improve soybean crop production in the Midwest to optimizing rocket engines. I mean, that speaks to the general application of design of experiments. When I went back to get my degrees in statistics, and I did focus on design of experiments, response surface methodology, it was not a replacement. It was an addition to my subject matter expertise in engineering and physics. And it's opened a tremendous amount of doors. And I'm going to share some of those examples with you. So I come back from graduate school, and my first project given to me is to characterize the world's most powerful solid rocket motor. Now, how's that for your out of the gate, first project? Let me tell you a little bit about the big picture here. The idea is that NASA was designing a new spaceflight system called the Ares 1. And the plan was to leverage historical architecture from the space shuttle. One of the solid rocket motors that, if you've seen the shuttle fly or seen a video, peels off at 120 seconds into flight. Well, the idea was to use that as a single stick configuration. And there were performance characteristics that were never important to know for the shuttle. But in the single configuration, one in particular, a rifling motion, a spinning of the rocket about its own axis, had to be characterized in order to control the vehicle in flight. And so the plan was take the rocket, lay it down on its side. That's the third picture over there from left to right. It's bolted to the ground really well. And the flame deflector is the side of a mountain in a test facility in Utah. And that is a full-scale, 12 feet in diameter, 120 feet long, at the time, the most powerful solid rocket motor in the world. And we want to characterize its performance in flight in this ground test facility. Design of experiments came in to characterize the test facility and to estimate the loads during the testing. And you'll hear a theme throughout my talk that measurement system characterization is something that I've always worked a lot in. Design of experiments is a fantastic tool for that. More specifically, this was a 5-factor experiment. It involved restrictions on the combinations that were possible and the level of those factors. I know a lot of people, when they take an intro DOE course and they see things varying between +or -1 and they go, I can't do that. I've never been able to do that in practice at NASA. You know, that's life. And that doesn't negate the tools, the powerful tools and concepts. It involved a second order response surface model that had to be inverted in order to estimate the loads during the testing. So what's really nice about this one is the picture on the far right, where we were able to do a flight test and confirm our predictions. And so that really forms a nice bookend. I will say, you know, while this wasn't the best easy baby step into applying DOE, it did get extremely high visibility in the agency and was a promoting factor for demonstrating the benefits of design of experiments at the time. It was something that led to many more people becoming interested in applying these tools. So now I want to give you a couple of quick examples, and I have papers at the bottom that if you want to read more about it, about these particular applications and how design of experiments was used, you can look those up. The one on the left involves a blended wing body aircraft. And along the back edge, you'll notice all those little words and pointers. I'm not sure if you can read them on your screen, but they are the control surfaces distributed all along the trailing edge of the flight of the wing. And we wanted to conduct a wind tunnel test to characterize the performance of this vehicle. And you can think of every one of those control surfaces as factors. Not only the control surface itself, but the angle at which it's deployed. Now, you can quickly look at that and see that to change one factor at a time is not only not a good idea, it's just plain infeasible, without many assumptions that limit what we could learn from the experiment and what we may not learn about synergistic combinations of factors. So this was a really good example of this high factor space to be able to explore. And I'd encourage you to take a look at the paper if you want to know more. Picture on the right is a powered wind tunnel test. That's an Army scaled helicopter mounted on a post in a wind tunnel at Langley. And the rotor at the top is actually powered during during testing, much like it is in flight. There's a pilot in the control room who flies, quote, flies the vehicle. He responds to the wind tunnel conditions changing. And this is the most expensive form of wind tunnel testing, powered testing. Cost per data point is extremely high. And so that provided a natural opportunity to demonstrate design of experiments. And I will throw in both of these, and this is common in a lot of work that I do, are actually used to validate computational models, another layer or level of design of experiments. I'm not going to talk about today, but computer-aided experiments, virtual experiments. And these experimental test results are used to anchor or validate or calibrate those models. So now a couple of examples about measurement system characterization. The picture in red on the left is the outcome of that paper that I stumbled on in 1999. It's a patented system that has saved NASA about $500,000 a year sustainably by reducing the time and effort to calibrate a wind tunnel balance. Wind tunnel balance is the primary instrument used in wind tunnel testing to sense the forces and moments. And so that system, is where I sort of began. I put it in my talk. On the picture to the right, the outline drawing was applying those same kind of ideas to 3-axis accelerometer packages. So from a design of experiments perspective, these were 6-factor, the one on the red is a 6-factor experiment with physics-based restrictions on the combinations that can be applied. And it was to develop a full second-order response surface model that can be inverted, like a classic calibration kind of example. I will point out that the paper in 2001. The third author, Draper, is Norman Draper. I'm proud to say that my first paper on design of experiments was co-published with Norman Draper, although truth be told, I didn't actually meet him in person for several years after that, but it's an interesting milestone for me. On the right is the development of an instrument that is used in atmospheric science to measure ozone, and in particular, an inexpensive instrument that can be put in the hands of middle school students all over the world to increase their engagement and involvement in environmental issues. And the design here was to develop a very low-cost spectrometer, one that is, quote, good enough. And you know, knowing when to stop is extremely important in the design of experiments. So once again, I will encourage you if you want to look more on those papers. Well, I wanted to put one slide in here about the practice of design of experiments and how much it depends on dialogue. To be application focused and to solve the right problem is a distinction of design of experiments. As I said, it starts with questions and not data. And George Hellmeyer has something known as Hellmeyer Catechism. He was big in the Department of Defense early, the predecessor of DARPA, and also the development of the LCD monitor. And he would ask these questions to curb the enthusiasm of a researcher. I don't know how many people work with researchers, but they want to test everything. They want all the data in the world. And they got to balance that with the cost. Well, that's the project managers who always want more money, more time, more people. And so finding that is something that he would use to scope the project. We can think of it in design of experiments terms, and I've converted these questions into a framework that helps us design an experiment, to know what the factors are and the objectives. And so many times I have people come into my office who are, well, sometimes they're sent there because they've tried a lot of times on their own to get the answers. And they come in and I ask them what it is that they need to know. And they usually say, I need to build this test article. I need to put it in this facility for this many weeks, and I need to get this data. And I say, no, that's not really what you need. And they look at me sort of dumbfounded, like they're in the wrong office. And I say, those are a list of things to do, but I want a list of things to know. Because we never subject ourselves to the cost of experimentation unless we're going to confirm something we think we already know, or we're going to discover something new. We don't conduct experiments to get data. Yes, data may be a necessary product of, experimental testing. We all know that, but that's not the point. It's just get the data, it's to learn. And so then I start to pull at that, and what comes out are things like, well, I need to test the performance of this vehicle, and I need to characterize this performance metric over these environments. And this starts to sound like factors. It is, it's in disguise. If I asked them what factors, they probably wouldn't know how to answer. So they explain it to me and I say, okay, well, how will you know when you're done testing? Now I get deer in the headlights. Look again. Some people would answer when I'm out of time and money. That's an answer. It's not a very good answer, but determining how well you need to know is linked to consequences. I've had the privilege to work on everything from early concept development to human spaceflight. And while nobody wants to be wrong about performance or decisions, it can be tolerated in early concept development, and the acceptable risk for human spaceflight is much, much less. And so that scales the volume of the experiment, the complexity of it, the cost. And ultimately, you see my last question is, can we defend the cost that's being put forward? And if you can't defend the cost, or if you need more, then I ask the subject matter experts to go back and rescope what they say they can learn with the cost they have. Just trying real hard with the funds you were given and failing is not noble. If I can tell you in advance, you can't answer those questions. So design of experiments provides a framework, and behind all of this conversational questions gets to the heart of designing an experiment. And these apply throughout the entire life cycle of a vehicle as well as components. So I want to close with kind of quickly a little bit more detail on one example, and this has to do with the Mars Curiosity rover. This was launched in November of 2011, landed in August of 2012. It was the largest rover landed on Mars. It's very similar to the current one that you hear so much about, Perseverance. It's the predecessor to that. It's shown in the upper left, folded up behind the heat shield. And the objective of this was to refine computational models that predict the target, the landing target, known as the landing ellipse. As you might expect, scientists want to land in very interesting places, craters and near mountainsides. Engineers want to land in big, flat, open deserts. That minimizes risk. And so there's this landing ellipse that is developed before flight. And we wanted to take measurements during entry, descent, and landing by putting instrumentation on the heat shield. Once again, there's a paper at the bottom you're welcome to look at and read more of the details, but that involved characterizing that experiment over a series of conditions during flight, but also to estimate the coefficients of that measurement system. This is a graphic that shows the area of flight from the time that we hit the top of the atmosphere, just before the heat shield is deployed. This is known as entry, descent, and landing. There's a great video, if you want to Google it, called 7 Minutes of Terror. That is entry, descent, and landing. It is the most complicated, worrisome, we'll call it, piece of putting something on Mars. And that's where this instrumentation was going to operate. The experiment involved 3 factors: pressure and 2 temperatures. And it involved how those pressures changed over time during entry, descent, and landing. And that's what you see by the ascending and descending hump that looks a little bit like a distribution there on the plot on the right. And also the temperatures, both the start temperature, which depends on where the vehicle was relative to the planet at the beginning of entry, and how the temperature changes throughout flight. And so this was broken up into 2 spaces, the temperature space, and this is a picture of that design. It's a hexagon design, a common response surface design, 5 levels in one direction, 3 levels in the other in the temperature space. And that was to estimate the coefficients. And then the points you see going diagonally are ones that confirm the most likely flight conditions. So they're confirmation points. And so this design superimposes the ability to estimate coefficients, to do confirmation, and the most likely flight trajectory. This is a very common technique that I use in many of my projects, to superimpose those in one design and use the points in different ways. And it's largely because it's so expensive to set this experiment up. This is a vehicle that's in components that are in a vacuum chamber, manned by a person 24/7, changing these temperatures. So you have to get it. It's an opportunity cost to get the points that you want to get at the time. Now, once the temperatures are set, then we change the pressures. And you think, well, how complicated can that be? That's just one factor. Well, changing the pressure is to characterize it over its full range, shown in the upper left, but then also a very specific region of interest, which is in the lower pressure range. And so there are 2 designs here superimposed over 2 different ranges. There's also mixed in confirmation points, maximum points, and some random confirmation points. And so this is known as a split plot design, where we randomize the order of the 2 temperatures, and then at each one of those whole plots, we vary the pressure in a random order. So a restricted randomization design, and those are very common in practice. Now, I told you at the beginning that one of the radical ideas was estimating models and coefficients. For me, when I was introduced to design of experiments. Well, the next step is to be able to interpret those coefficients into the subject matter's experts' language, into their vernacular. And this is an example. I'm not going to read you all the words on the slide, but each one of those coefficients, there's an explanation of what it means, what it represents, whether it can be updated in flight, whether it can be assumed to be negligible based on our physics of the problem. This is very powerful in terms of being efficient in experimental design, is thinking about postulating models and thinking about what we have to capture, what kind of behavior, and what all those terms mean. They're betas. They're just betas in statistical terms. They become useful when they're in subject matter language. And as I've pointed to a couple of times, measurement system characterization involves this forward modeling, which I've shown here at the top, where voltage of the pressure transducer is a function of pressure and two temperatures. And in flight, we have to partially invert that relationship to estimate pressure as a function of voltage and temperature. And we have to do it with uncertainty because it's going to get rolled into the overall flight reconstruction. So not just deterministically solving linear equations, they are with statistical uncertainty, and that's the power of how we design the experiment, how we estimate the coefficients. Now, I want to throw in one other twist to this one, which is we use some statistical process control tools because, as I told you, it takes about 9 months to get to Mars. And the question would be, is our calibration model developed on Earth still going to be valid when we get there in 9 months? Or is there going to be drift? Is there going to be changes over the environment of flight? By having a model, having coefficients, defining what those mean, we can think about different ways that they might change. We can also think of clever ways to determine those right before entry. And that's what we did. We came up with ideas to do that. But on Earth, we did some long-term experiments. And this is an area of statistical process control known as profile monitoring. It's a very simple application of it, very simple picture of it, but it meshes very well with the design of experiments. And then lastly, I just want to point out that the experimental measurements were going to be combined with computational models in order to do flight reconstruction. So at the top, measured flight data, that's the experimental data. Predicted flight data, that comes from computational models. If you follow the path on the far left where it says pressures, that's what I've told you a lot about. And you'll see a dotted path where it combines measured pressures with predicted pressures to develop the pressure-based reconstruction. The rest of the graph and the point of it is to show there's other ways to do this too. And guess what? They don't all arrive at the same answer. And so that reconciling is very important based on the rigor of how we get to each of those individual ways to do the flight reconstruction. So with that, I just want to offer a couple concluding remarks. I hope you can feel my excitement about where design of experiments has been used at NASA. And I think of design of experiments both in the philosophy level of asking questions, deciding what we're going to do with the data before we get it, postulating models that inform how we design, and then methods. I didn't talk a lot here about like factorial experiments or fractional factorials or those things, but those are the methods. Both are important. And over the last 25 years, it's really had significant impact. My second point is to emphasize it's a team sport. Design of experiments on the kind of problems I work with are always multidisciplinary. And I think that design of experiments offers this really nice framework to communicate multidisciplinary wise statistical concepts, and if we can put it well into the subject matter experts terminology. And then lastly, I've told this story like a big success story, and I want to tell you there were some ups and downs organizationally in getting design of experiments infused. For those of you who are in that condition, I would say successful demonstration is what gets more adoption of design of experiments and more people interested in refining and growing their discipline, their expertise in the discipline. And so with that, I'm going to stop, and I guess I'll stop sharing my slides.
Thank you, Pete. This has been an extremely interesting presentation. I really enjoyed this. And in fact, I'm going to go and track down some of the papers that you cited here, because I definitely would like to read them. You've addressed something a couple of times in your presentation, that I'd like to talk a little bit about. And you pointed out that that successful application often encourages broader use of the methods. And I'm glad to hear you say that, because that's something that I've experienced a lot over the years that I've been involved with experimental design. When the first edition of my experimental design book was published back in 1976, well, that seems like a long time ago. It was really the only book around on experimental design that was aimed at engineers. And because of that, the book got a fair amount of attention, and I started to get phone calls from people at different companies to say, well, would you come and teach people in our company about how to do this? And I got kind of lucky, I think, with that, because I had learned experimental design from Ray Myers. And Ray always brought really fascinating examples into class. And I'm sure your time at Virginia Tech, you interacted with Ray a lot also, and you know exactly what I mean. And so when I agreed to do a class for somebody, I said, okay, I only want you to send people to this class that already have an application in mind. They have a project, something that they want to apply this to. And I always taught the class in 2 sessions. I would do an introductory part of the class, which would be about 3 days. And then I'd wait a month or 2 and then come back and do another 2 days. And part of that was having these guys talk about their application. What had they tried to do? And an awful lot of these people went on to have big success with applying the methods. And suddenly it seemed that people throughout that company found out about the applications, and then they were clamoring for another course. and it got to the point that I was doing a lot of these, but to me, it was that one successful application can really turn it on in an organization. And it seems like you've had exactly that same experience.
Yeah, that's very much true. The first one I showed you, the solid rocket motor, testing, that was
Right.
Agency level. We had the NASA administrator asking regularly how that was going. And interestingly enough, we received a group award for all of the folks that worked on that, NASA headquarters, and I was the one that received it.
That's great.
As a statistician, standing next to the NASA administrator and the associate administrator is not the position that most statisticians would enjoy. and it was because of the impact of that project. It reduced system uncertainty. It was very, impactful, and got a lot of attention about design of experiments. And that did lead to others coming to the center, to NASA in general, and courses, educational targeted resources, all of those things
Right.
were brought. And it's the demonstrations, whether people fully understand it or not at that stage, that really makes the biggest impact.
It's really, I have found that to be the case a lot in my practical experience, that one success does a lot. And it's even happened not only in my consulting practice, but in my academic career, because students take my graduate level course in experimental design, and then they want to try to apply that in their thesis and dissertation research. And suddenly I found myself on dissertation committees in electrical engineering and material science, and all sorts of different areas. And the faculty over there get kind of excited about this and say, well, gee, I'm going to send more students to take your course, which is fine. I teach my graduate course in experimental design every semester, and I usually have between 75 and 100 students, sometimes even more. I've had as many as 150. And I have an online version of it, and well, in addition to the MOOC. But I think that's really an important point that the participants in our Coursera course can grab hold of, is finding a way to have a home run. Finding a way to have a home run can really stimulate interest and excitement and enthusiasm about using these methods in your organization. And as I'm fond of telling a lot of people, if you're not doing this in product development and process development and characterization, you are leaving money on the table. You really are. And particularly when it's new product development in the commercial world, you're leaving the door open for competitors to put you out of business.
Right.
And
it's an interesting situation at NASA in that we, this might come as a surprise, we're not turning a profit this year. So we have these different metrics, right? Not bottom line, but we have metrics to answer to our taxpayers of maximizing the value of every dollar we get. And so it's about knowledge and how fast we can get it, how efficiently we can get it. That has been an interesting metric, but it parallels obviously the bottom line and competition.
It sure does.
But casting the value of design of experiments, not on how much money we save or how much we've improved the bottom line, but how fast we can learn,
right?
How much faster we can get the answers we need.
Yeah, the speed at which you can develop a new product or a new process or a new system is vitally important in your world and in commercial products. I've worked with a lot of people that do biotechnology type pharmaceuticals, and that's a very competitive business. And the people that get there first are the ones that own the business.
Right.
And so if you're all working away on 3 or 4 companies on trying to develop a particular product to treat a particular health condition, getting there second doesn't help. If you get there first, you own the business.
Right.
And design of experiments can really accelerate the speed with which you develop new products. And that's really important. I have one sort of curiosity question about one of the slides that you talked about, and that was the helicopter in the wind tunnel. And you mentioned that the engine's running, the blades are turning. This is a powered study.
Yes.
Okay. Well, okay. I don't know a lot about helicopters. When I was in the Navy, I had a fear that they were going to make a helicopter pilot out of me because I didn't understand how they worked. I mean, I know, it's still Bernoulli, okay, but it's not the fixed wing stuff that I was used to, and so I understand why you need to do the powered test, but that immediately made me think about the Mars helicopter. Okay, don't you have to do testing for that at very low atmospheric pressure also?
Yeah, and they did. I wasn't personally, but yeah, you'll see where they did fly it in sort of a vacuum chamber arrangement. Yeah, absolutely.
Okay, and so that was, and probably they still did a powered test.
Right. So what's different about the helicopter I showed is that it's really an aerodynamic performance test, not sort of a flight test. And the rotating blade changes the flow around the body, as you might expect.
Okay.
You can't really characterize a helicopter the way you do a fixed wing aircraft. where it's more about the aerodynamics of the shape. It's not totally true. I'm oversimplifying a little bit,
Yeah,
but
but I think I
you get a
understand what you're
you get a
saying.
wake. You get a wake essentially from that.
Yeah.
And that particular test was about developing mission capabilities, in particular mission duration,
Mhm.
based on the performance of the vehicle and based on how many things you had attached under the wings.
The
Um,
other slide that you had that I thought was very interesting, where you were showing the airfoil with all of the parameters on the trailing edge of the airfoil, and I would think about it, doing wind tunnel testing with that device. The classical way would be to change every one of those factors one at a time, and
Right.
it would take forever to do the test. Uh,
it would just be infeasible, or without a lot of assumptions. I mean,
Yeah.
that's the way to say
Yeah.
it, right? You'd have
and
to assume a lot of independence of
and Ray Hill from Air Force Institute of Technology has done a lot of work on wind tunnel testing.
Mhm.
And I've worked with Ray on a couple of projects, and we worked with the people at Arnold Air Development
Mhm.
Center, and we basically showed them how they could reduce the amount of wind tunnel testing by like several orders of magnitude if they used factorial and response surface type designs and get exactly the same answers.
Right.
If you look at drag profiles and that's a lift and that sort of thing, you get exactly the same answers with instead of 1,000 tests, 90 tests. So
Right.
yeah.
Yep.
So
There's been many papers written out of Langley on,
yeah, I'm sure that you guys have had exactly the same sort of experience. Yeah.
but it still takes time for that sort of mode, I will say, to still become prevalent. I don't know, it's new, right? It's a new
Yeah.
idea compared to the way they would do it before. And interestingly enough, the performance metrics before would have been things like how many data points can we get per hour,
Hmm.
instead of how many data points do we need.
Right. Right. Yeah. Pete, we got a couple of questions that we ought to take a look at, and the first one is it looks like it's addressed to you, and it says, I think you talked about simulation-based design of experiments, and can you please share some references about some such experiments? And I would love to understand how it could be used as complementary or supportive study before we can execute a physical design of experiments. Do you have
Yeah.
any thoughts on that?
Yeah. Computational experiments, in my mind, are still experiments, right? We're still trying to find factor response relationships.
Exactly.
So the philosophy is the same. And what questions, what do we need to know? What's different about computer-based experiments is most of them that I deal with are deterministic in nature, not stochastic. And so the idea of replication doesn't necessarily make sense. And and I will tell you that, originally when computer experiments came out at NASA, and people thought, well, this is going to replace the physical experiments because running computer experiments is so much cheaper. Well, that's not true. Computational computer experiments can be just as expensive as physical experiments. And so there's still a desire to get, a small number of points. The whole area of design and analysis of computer experiments, I do have some work that I've done in that area. I didn't highlight it in this talk. And I always think of it as being complementary to physical experiments. It's funny when I get into these meetings, the experimentalists believe their data are right, and the computational folks believe their data are right. And I usually sit down and say, you're both wrong. You're just wrong in different ways. And combining them together is how we get the most realistic representation of what's going to be an actual flight performance. And so I always think of that as complementary, one feeding the other, and set up the experiment in that way, because there are certain points or combinations or responses that lend themselves well to computer experiments, and there's others that lend themselves well to physical experiments. And there's certain underlying assumptions on the test facility, the physical test facility, and there's certain underlying assumptions about the computational code And so understanding that integration is an area that I spend a lot of time, sort of working to merge both and not work on one or the other. But, the concepts of design of experiments come down to how many points and which one.
Right.
And those are the same questions for computer experiments. And we have a whole new set of tools and designs that lend themselves well to computational experiments. Space filling designs is a whole area.
We actually talk about that in the course.
Yeah.
We have a couple of lectures that talk about space filling designs and the various kind of model fitting schemes that you can use, and it is an important area. It really is, because so much of engineering design is with deterministic computer models, finite element models, for example.
Finite element, computational fluid dynamics.
Exactly.
Yeah.
So here's another question. So is it necessary to do replication samples in a mixture experiment? And my response to that would be yes. I think you do want to replicate some of the runs because you always want to get some idea of how big is the experimental error.
Yep.
And mixture experiments can have can have random error, just like any experiment. And so, yeah, I think that that you always would want to think about replicating some of the test combinations in a mixture experiment. Maybe not all of them, but you certainly want to replicate some of them. And
I'll throw in there that replication, as I made my joke about the engineer that said replication causes error.
Yeah,
replication is one of the most powerful tools of design of experiments.
That's
To
right.
explain to somebody that when you set all the factors to the same, the best you can, and you get a different response, that's independent of the models.
Yep.
It's independent of the design.
Yep.
That is so powerful to communicate. I think it's often overlooked, the idea of pure error.
Yeah, it's valuable information.
It's very valuable.
Yes. Yeah. And if you go from a development environment into a production environment without some understanding of how much error there might be in the system, you are going to get some nasty surprises from time to time. And so replication is always a very valuable idea. Okay, we got another one. I think this is a more situational question. Let me read this one, Pete. Why does lack of fit of a model significant when the pure error is small? Does it mean that higher noise levels, significant difference in response at the center points is better? I ran an experiment on leaching of metals, and my lack of fit was significant. I went through several articles on leaching and observed that their lack of fits were insignificant because the values of the response variables at the center points were significantly different. Currently, it is looking like I have to choose between lack of fit and high R-squared value as a measure of the adequacy of my model, which doesn't make sense because both are meant to agree. I forgot to mention that the experiment was meant to optimize three factors using a central composite design, face-centered design. I also tried using alpha of 2, but still experienced significant lack of fit because the values of the response variable at the center point were very close.
Yeah, I could comment on that if you like.
Please do.
Yeah, so I told you a lot about calibration experiments, and and those characteristics, R squared is always near 1 because that's a good designed, well-designed instrument. And so we have extremely low noise levels. And so this sort of challenge between lack of fit being significant, is an area that I've spent a lot of time thinking about. And I think there's this practical lack of fit versus the statistical lack of fit. As the pure error goes to 0, lack of fit goes to infinity.
That's right.
And so I think this is one of those cases, and I don't know this specific application, when you seem like there in the question, there's some tension between you're not captive to the statistical test at the moment. Maybe there's my freeing comment. Think about whether that lack of fit is practically significant, not just is
Exactly
statistically significant.
Yeah. How bad is the lack of fit?
Relative to your objectives.
Exactly. And this is a place where confirmation testing could be very useful. Find a point in the design space that you're interested in, use your model to predict the results, and then actually run a confirmation experiment at that point and see what kind of agreement you get. And that'll give you some ideas about whether the lack of model fit is a big deal or not. Confirmation testing can be really useful. Pete, we've come to the end of our questions, and we're also coming to the end of time. So we're going to have to quit. And okay. I want to tell you how much I appreciate this talk. This was a fascinating talk. And I'm going to track down some of these articles and look at them myself, because some of them I'm not familiar with. I really appreciate your taking time to do this. This is the end of today's session for those of you that are at the Fireside Chat. The next one is scheduled for Wednesday, April 6th. And more information about that, the topic and what we're going to talk about will be included in the course. So you'll find out more about that later. Thanks for joining. I appreciate you coming. And once again, thanks to our guest, Dr. Pete Parker, for a fabulous presentation. Thanks again, Pete.
Thank you for inviting me.